por aquí.
Pues si quieren ya podemos dar inicio a la presentación de Michael. Michael está en el 11º cuatrimestre. Michael, ¿tu presentación es en español o en inglés?
For today, I would like to make in English.
Ok, al menos nos entendemos al hablar. Bueno, si quieren, ya le damos la palabra a Michael. Michael, tú estás en el 11º cuatrimestre, ¿verdad? You are in the 11th quarter?
Yes, that's the 11th now, yes, ma'am.
Ok. Bueno, pues entonces empezamos, por favor, lo dejamos que presente sin interrupción. Tenemos aquí la opción en Teams de levantar la mano para hacer preguntas, pero lo haremos al final, ¿no? Michael, buenos días y puedes empezar.
Okay. Good morning. I'm going to be presenting my advances on the work. My topic is copper indium selenide deposition. I'll be working with three-stage method and the study of the post-deposition treatment with alkali halides. And then this will be the summary of the contents of the work I'll be presenting. First of all, the introduction has to do with the need and the motivation needed for the alternative energy sources due to the continuous increase in demand for energy. And then all over the globe, the common source of energy, as we know, is fossil fuels. And currently, Mexico, also being a member of the Organization for Economic Cooperation and Development Countries, has joined in the race to provide alternative sources of energy that will help to reduce pollution and then also avoid the potential risks associated with the use of fossil fuels. And there are other sources of energy now being exploited, like biogas and solar energy. Among all these energy sources, the solar energy has continued to be the one that attracts a lot of attention from many researchers because of its relative high abundance. And then it's also green and it is noiseless. As you can see from the figure 3, that Mexico lies within the range of the equator known as the solar belt zones, which has tremendous amount of solar energy incident on the surface of the Earth. And to tap into this numerous amount of energy that is available, the photovoltaic systems have been useful in converting the sunlight directly into energy with no pollution and no noise. And also, due to the continuous increase and interest in this area of research, there's a continuous decrease in the manufacturing cost, and the solar cells being fabricated are continuously increasing in efficiency. So that adds to the allure or the advantages of tapping into this source of energy as the alternative. Then for this study, if we look at, even though Mexico and other parts of the world are positioned to tap into this source of energy available, a quick look at the percentage of energy being generated in this case, using example Mexico as a case study, shows that they still depend massively on fossil fuels, with only about 0.72% of the energy being generated from solar energy. That means that much work needs to be done to tap into this numerous available source of energy. And then for this study, we'll be focusing on the solar cell fabrication. Specifically, the goal is focused on the fabrication of device-grade CIGS absorber layer for solar cell application. Also, we'll be studying some of the beneficial effects of using heavier alkali metals on the CIGS layer. Objectively, we'll be depositing and optimizing the molybdenum back contact and also the transparent conducting oxide layer of AZO. And we'll be depositing the CIGS quaternary alloy using the co-evaporation study method and study the effects of post-deposition treatments using the heavy alkali metals And finally, we'll be looking at the study of the interface properties of the different layers with the aim to improve the efficiency of the solar cell that will be fabricated. Looking at the solar cell model we have in mind, the figure 6 shows the solar cell model that we're proposing, where we have the back contact, molybdenum, the conventional CIGS material, that will be the absorber layer. The buffer layer is CDS. But in this case, we hope to introduce an embedded layer of alkali metal between the absorber layer, which is CIGS, and CDS. In this case, we are looking at modifying the interface between these two layers. Specifically, we are working on CIGS, the molybdenum. Previous works have been done by my colleagues in the lab on CDS, which has been published, and also the intrinsic zinc oxide. Also, we'll be working on the aluminum doped zinc oxide for the TCO layer. Previously in my work, I have worked, and also during my pre-doctoral presentation, I presented the work we did on the molybdenum back contact, which has been extended also to flexible substrates with barriers. And a quick look at table 1 shows the results that we obtained by optimizing and developing a new method for the back contact layer, which we developed a bi-layer model. And figure 7 shows a cross-sectional image. We also worked on the TCO layer, AZO, and which table 2 shows some of the results for the best conditions that we observed, and the quality factor which we defined for these materials. The table 2 shows the values that we got. On the flexible substrates, we're able to optimize the conditions for fabricating the back contact on stainless steel as the substrate, and optimizing the different barriers, we're able to calculate the percentage reduction in impurities that usually come from the back stainless steel into the absorber layer, which reduces the efficiency of the solar cell. So these are the previous works that we've done. For the new work that we're going to do, which we have done within the past year, we've been working on the CIGSe absorber layer fabrication, adopting the thermal deposition method, which has temperature as the key variable that influences the evaporation rates after optimizing the chamber conditions. The temperature, as well as the different evaporation rates, will affect the final composition of the material. And then under this thermal deposition method, we will be adopting the co-evaporation method, specifically the 3-stage deposition method, which has several advantages, which include the versatility and the feasibility to scale it up for large area device productions. It is economic in comparison with other methods such as an MBE, and comparing also with other methods is relatively less expensive, and high purity materials can be obtained even from so pure elemental sources due to the different evaporation rates, evaporation sources. And for this, we're working on CIGS, which we already know it has different advantages as for application in solar cell, which includes its high absorption coefficient. The bandgap is tunable between 1.0 to 1.67 electron volts with gallium variation, and also recently with application of bandgap engineering and sulfur incorporation, it can also be increased up to 2.4 electron volts. It has relatively high stability, and the efficiency keeps increasing with research. And right now we have about 23.4 conversion efficiency in the use of this material. The deposition we'll be adopting will be the deposition using the novel 3-stage method, and subsequently a ramping method, using a selenization rather, using a ramping method. So after the CIGSe absorber layer deposition, we intend to deposit and do a post-deposition treatment. The post-deposition treatment mainly recommended and has been applied for this absorber layer material using the alkali metals are done in 3 different major methods. The pre-deposition, which can come from, example is the soda lime glass. In that case, the alkali metals are already available before the deposition. In this case, that's what is referred to as the pre-deposition. Example is sodium from the soda lime glass, or in some cases, there are molybdenum back contact layers which are doped with sodium, which when heated, the sodium will now diffuse into the absorber layer. Or the co-evaporation method, which between the stages of the deposition, between maybe first or second stage, the alkali metal is being evaporated into the absorber layer. And finally, the post-deposition treatment, which is usually applied for heavier alkali metals. In this case, we are referring to cesium and rubidium. Now, the common method of employing this post-deposition treatment for the heavy alkali metals are using the vacuum method. After the deposition of the CIGS layer and selenization, there's an evaporation of this heavy alkali metal in form of fluorides, but with heat treatment, the fluorides tend to evaporate, leaving only the alkali metals behind. But in our study, we are trying to propose a new method, employing a non-vacuum method for depositing these alkali fluorides, in this case, using the spin coating method. And then after that, we will be applying some heat treatment to remove the organic residue or solvents attached, and then to be left alone with only the alkali metals. And then for this study, we intend to deposit the thin layer of the alkali fluoride using optimized parameters, and we'll study the effect. Now, previously, all the studies have been carried out on the alkali metals are mainly on the lighter alkali metals. In this case, we are referring to sodium and potassium. But recent studies are focusing on the heavier alkali metals. And unlike the lighter alkali metals, which have bulk effects, the heavier alkali metals are usually don't necessarily diffuse into the bulk of the material, but rather they are found at the surface. So they apply only at the grain boundaries and the surface modifications to improve the functions of the efficiency of the solar CIGS absorber layer. This gives a schematic of the evaporation chamber we are using for our evaporation in the figure 9, where we have our 4 sources for the metals, source metals. And well, from our study, we tried first of all to find out for our chamber to optimize the deposition rates of the different sources given in table number 4. And you can see the different materials, the temperatures, and the evaporation rates. Now, from the table 5, to avoid so much repetition, but to have an idea of what our composition will be, we have estimated the compositional ratio, especially between indium and gallium, which was targeted to give us the desired band gap, which we are targeting, in this case, about 1.2 electron volts. So a comparison of and calculation of the evaporation rates, calculating the ratio, can give an estimate on idea of the best temperatures that will serve as the sources, in this case for our evaporation. And then based on the previous calculations and estimates we made, we adopted the different source temperatures. Copper, we evaporated at 1,300 centigrade, indium 900, gallium at 1,000, and at all cases, we are evaporating our selenium at 200 degrees centigrade. For our deposition, the first stage will be indium and gallium, second stage copper, and then our third stage will be indium and gallium. And like I said, at all times, the selenium will be allowed to be evaporating. Figure 10 gives a schematic of the adopted deposition technique. And now the aim of this is to try and obtain a band gap of about 1.2 electron volts with a slightly copper poor composition. Figure 11 shows the schematic of our ramped selenization method that we used for the selenization of the depositions. And after the deposition, for our post-deposition treatment that we've proposed, in this case, the spin coating method, and we know that this method depends on some factors, including the speed, viscosity of the solution, the spin time, the density of the solution, and then after the deposition, the sample is being annealed to remove the solvent being used so that we'll get our film back. After some works, we are able to optimize the solvent that we used for our work. In this case is isopropyl alcohol, and the optimized molarity is 0.3 molar solution. Now, in this case, if we try to increase the molarity, we end up getting a gel instead of a film, because the film will now not be dry. And also, we notice that this film is highly hygroscopic. So in that case, increasing the molarity and getting a very thick layer will only absorb more moisture from the atmosphere. And for our deposition, in all our works, we deposited in nitrogen atmosphere to avoid contamination from other ambient gases that might be around. And then the spin duration that we optimized was about 45 seconds. We dried the samples after deposition at 350 degrees centigrade within range. And after some studies and different results, which I just presented here, the optimal condition that we used, the film thickness, average film thickness is about 39.73 nanometers. On glass, to verify the composition of the alkali metal that we are depositing, we present the table 6, which presents the EDS composition of the analysis, and where we have about 99% atomic percentage cesium and 99.04 atomic percentage rubidium, justifying the use of the name alkali metal instead of alkali fluoride within our CIGS layer surface. This presents the ideal bandgap that we are hoping to achieve. Now, for every CIGS highly efficient solar cell, the bandgap, or it's expected that the surface provides an ordered vacancy compound, which refers to a slightly copper composition layer at the surface. In this case, by providing this alkali metal surface, we are also inducing more OVC layer on top of the structure. And the figure 13 shows the band diagram for the CIGS, including the ordered vacancy layer. And we can see that we are limited in our size of the ordered vacancy layer, because so much size of it will reduce the space charge region, which is not good for the solar cell. So we have to keep it to a minimum that will be beneficial to the solar cell, as well as help to improve the carrier collection and reduce recombination. First of all, we try to optimize the result on CIS first before we will move into alloying the CIS material with gallium. And there, the result here shows the CIS result we obtained after deposition at the different source temperatures and annealing at 550 degrees. We see that we were able to obtain all the peaks corresponding to the chalcopyrite structure, and the crystallized size varies, but goes back to increases with the time. The CIS 60 refers to annealing the CIS material at 60 minutes, and 90 minutes, and then 120. And then the table 7 provides the different parameters that we are able to, we calculated from XRD. And the 2 theta value, the FM, the full width half maximum value, the crystallized sizes increased, and then for further increase in temperature, it slightly showed a slight decrease. This the value of T shows the thickness while the delta sign is the dislocation density, and then N represents the crystallites, number of crystallites per unit area, which depends on the crystallite size. And then we try to take some same images and calculate the atomic percentage compositions for the different values. The average composition shows that we have about 1-to-1 ratio of the copper to indium. For 60, this is an average of the different points for different times. So we have about copper to indium ratio is almost 1 in all cases. Also, when we try to check the AFM, surface topographical analysis, we saw that the peak-to-peak value especially tends to increase with higher annealing time, and the roughness also tends to increase. So the roughness tends to increase with the annealing, and then when we try to go to the Raman, all the films show the A1 mode corresponding to the charcoal pyrite structure. The table 9 shows the resistivity value, carrier concentration, and mobility measured from the Hall measurement. All the depositions show the A1 mode of the Raman spectra. And then the slight variation that may be observed in the peak position might be due to a small variation in the composition. So using this value from the CIS, we moved on to alloy the CIS compound with gallium. And then from the source temperatures, the gallium was evaporated at 1000 degrees centigrade. And now this shows the figure 18 shows the result from the XRD measurement. Now, in this case, one important thing we tried to do was to avoid presence of any other elements, maybe due to surface treatment. We just characterized the samples. After the deposition of the CIS, we carried out our surface treatment, post-deposition treatment using cesium fluoride and rubidium fluoride, and we did not carry out any other surface treatments, so that we will study the effect of these alkali metals. And from the XRD image shown in figure 18, we did not observe any other secondary phases that might belong to the alkali metals being formed with the CIGSe material. We, however, observed some secondary phases of CIS, which is expected between, for this formation of CIGS, there's a probability to form the secondary phase of CIS. But we also observed a peak of copper selenide, which tends to decrease with post-deposition treatment, maybe due to the effect of the treatment, but it tends to decrease. But like I said, we observed no other secondary phases belonging to the alkali metals. From the same image, we can see that the image shows an increase in the grain sizes after treatment compared with as deposited sample in figure A, 19A. In the B, after the cesium fluoride post-deposition treatment, the grain sizes increased, and then in C, we also saw that we also saw that with rubidium fluoride treatment, the grain sizes also increased. Now, this increase in grain sizes is desirable because it helps in passivation of the grain boundaries, and this is reportedly beneficial to reduce recombination losses at the grain boundaries. Also, an important observation we made was in the EDS composition, which we saw that the copper content decreased from 1.0 to 0.9 to slightly lower composition after the post-deposition treatment, in accordance with the expectations of OVC layers. And also, the indium content tend to increase slightly after the post-deposition treatment. The gallium change in the gallium content might be due to the temperature effect, because we know that gallium tends to migrate towards the back contact with surface treatment. So the EDS analysis here shows that the obtained result is in accordance with the expectations. And this result here, we have in figure 2B. Maybe I saw a large grain structure. Well, after the deposition, usually the surface of the material is maybe rinsed with water to remove any residual particle. In this case, the large grain or the large grain structure that we have here might belong to just a residual particle that can be rinsed away and not really part of the grain. For the band gap, first of all, we just try to estimate the band gap of the as deposited structure, and it's giving us from tau plots. Extrapolation shows about 1.18 electron volt for the band gap. But we try to use the formula given to estimate the band gap, considering the gallium composition, the Bowling factor, which we use as 0.15, and the band gap. EG will give the band gap which we are looking for. In this study, although the optimal band gap of the solar for the absorption of solar spectrum was about about 1.45, but solar cells from CIGS material have their optimal performance around 1.2 electron volts. In this case, we desire to have a band gap of our material to be around 1.2. And then the table 12 shows, considering the copper to indium gallium, considering the indium to gallium ratios that we obtained in our EDX measurements, we try to calculate theoretically what the band gap will be. And then we have that for axe deposited, the estimated theoretical band gap is about 1.24. While that of the cesium fluoride and rubidium fluoride, in this case, copper and with cesium fluoride, cesium deposition and rubidium deposition, the band gap is about 1.22 and 1.15. For the surface treatment, for the grain analysis and surface parameters from AFM measurements, the area of the grain remains the same, but we observe and made an important observation here that the peak-to-peak value reduced significantly after the post-deposition treatment from 2.057 to about 0.77. So this shows a significant reduction in the peak-to-peak value. And also looking at the image, we saw some forms of smaller granular structures attaching to the bigger structures. When we try to take the Raman measurement, all the films show the peak position corresponding to the A1 mode as well as the B2 mode of the charcoal pyridite structure. But if we look closely, the position, the sample with rubidium and cesium post-deposition treatment showed a shoulder. Now, previous results say that the OVC layers have a shoulder in the CIGS structure using this Raman around 150. But that is only for the copper pore composition. But in this case, we tried creating another layer on top, which in this case, the shoulder we are seeing here can be attributed to the OVC layer created by the presence of these heavy alkali metals, in this case, rubidium and cesium post-deposition treatments. So the slight changes that may be observed in the peak position also can be attributed to the different compositions. Another observation we made was on the Hall measurements. Now, importantly, we saw that the carrier concentration significantly reduced from 10 raised to the power 17 of the power to about 10 raised to the power 14 after the post-deposition treatment. Now, this, can account for the maybe significant loss in the VOC, but what was lost in the VOC of the solar cells after the fabrication can be gained back due to the increase in the mobility. We can say that the mobility increased to about 50% and more after the post-deposition treatment with these metals. Now, previous results on surface treatments of these using these heavy alkali metals show that the heavy alkali metals add to the efficiency of the CIGS layer by surface effects. Surface effects, as we can see as we saw in the grain structures increasing in the same image that we produced, and also the peak-to-peak value that we saw. And that shows that these results can improve the interface between the CIGS layer and then the CDS layer. In that case, there will not be the heat generated between this layer, usually accounting for the lesser lifetime and damages due to recombination losses between the CIGS and the CDS layer, will be significantly reduced with this post-deposition treatment, which adds to the advantage. So the loss that we are going to encounter in the VOC will result in another gain in the JSC of the solar cells, and in that case, there will still be an improvement in the efficiency of the solar cell. So in conclusion, we optimized the source temperatures and the conditions for the deposition of the CIGSe material using the three-stage method. And after that, we developed and we proposed a new method for the post-deposition treatment using a non-vacuum method as against the conventional vacuum method that's been reported in literature. And we saw from the EDX measurement of this that we are still going to get back a high composition of the alkali metals, which accounts for our alkali metal layer inclusion in the conventional CIGSe structure. So we carried out these different basic characterizations to verify that these studies are viable to be applied in the solar cell fabrication. And then in conjunction with the results that we previously obtained for the back contact, the transparent conducting layer, and then previously reported or published values from our colleagues on the CDS layer and the zinc oxide layer, we propose to fabricate a solar cell using all these results. And then I've completed about 85% of my work. In this case, I've optimized all the layers that I need for the solar cell fabrication. The next work I have in hand will be to fabricate the solar cell using all these optimized conditions. And I've already made plans to start writing and completing my thesis, which I hope to submit by the next Cuatrimestre. I've taken some classes while in the course of my program. Some of the classes I've listed: characterization of semiconductors and the physics of semiconductors, as well as a class on the thin films, and then renewable energy and sustainability. Participated in the writing of a patent, and I've written and published some articles, and with an article that we hope to send very soon for publication. I've also participated in and presented works in some conferences while in the course of my study here. Thank you for your time.